March 17, 1945. The Rhine River, Germany. Lieutenant Colonel Harvey Fraser stood on the western bank, watching his engineers work under relentless German artillery fire. The notebook in his weathered hands contained calculations that defied everything the Wehrmacht believed about Allied capabilities. 27 hours. That's how long it had taken his men to construct a 969-foot floating bridge across one of Europe's mightiest rivers, while enemy shells screamed overhead. In Berlin, German High Command had calculated it would take the Americans at least a week to build such a crossing, assuming they survived the constant bombardment. They were wrong. Through his field glasses, Fraser could see German observers on the far shore, their binoculars trained on something they couldn't comprehend. Standardized steel panels, each weighing just 570 pounds, were being assembled by teams of 6 men at a time. No cranes, no heavy machinery. Just human hands, portable components, and an engineering philosophy the Germans had dismissed as impossible. The bridge was already carrying 40-ton Sherman tanks across the Rhine. What the German engineers didn't know was that this moment represented the culmination of a revolution in military engineering that had begun 4 years earlier in a small office in Christchurch, England. A revolution born not from complex machinery or advanced technology, but from elegant simplicity. The kind of simplicity that would prove impossible for German forces to destroy, no matter how many bridges they demolished, no matter how many tons of explosives they used. This is the story of how American engineers used modular design principles to build bridges the Germans couldn't destroy, how a British civil servant's hobby became the weapon that broke the Wehrmacht's defensive strategy, and how the simplest solution became the most powerful tool in the Allied arsenal. The mathematics of Allied victory were being written not in grand strategies, but in the portability of steel panels and the speed of their assembly. The Germans had destroyed thousands of bridges across Europe, from Tunisia to the Rhine. They believed they had bought themselves months, perhaps years, of defensive time. They were about to learn that American engineering ingenuity had rendered their entire demolition strategy obsolete. The crisis began in May 1940. Dunkirk had fallen. The British Expeditionary Force had escaped across the Channel, but they had left behind nearly all their heavy equipment. Britain now faced the prospect of defending an island against invasion, while simultaneously planning an eventual return to the European continent. The problem was stark. Every British military engineer knew it. Their existing bridges couldn't carry the weight of modern warfare. The Inglis Bridge, designed during World War I, could support just 19 tons. The new British Matilda medium tank weighed 23 tons. The Churchill heavy tank, still in development, would weigh at least 40 tons. American Sherman tanks, when they arrived through Lend-Lease, would weigh 33 tons. The mathematics were brutal and undeniable. Britain's entire bridge inventory was obsolete before the war had truly begun. At the experimental bridging establishment in Christchurch, a small team of civilian engineers gathered for an emergency conference in February 1941. The directive from the War Office was clear: design a bridge that could support 40-ton tanks across spans up to 200 feet. Make it portable enough to transport in ordinary trucks. Make it simple enough that infantry could assemble it under fire. Make it strong enough to withstand artillery bombardment. And have working prototypes ready within 3 months. The requirements seemed contradictory. Strong bridges required heavy materials and complex engineering. Portable bridges were light, but weak. Quick assembly meant simple designs, but simple designs couldn't handle modern tank loads. Previous military bridges required cranes and specialized equipment. The engineers had been given an impossible task. Donald Coleman Bailey sat quietly in the back of the room listening. At 39 years old, he was a civil servant with the experimental bridging establishment, known more for his meticulous attention to detail than for revolutionary thinking. He had joined the War Office in 1928, spending 13 years designing military equipment, pontoons, cranes, pile-driving rigs. His colleagues knew him as competent, thorough, and somewhat reserved. Few knew about his hobby. Since boyhood, Bailey had built model bridges from wood and string. In his home workshop, he tested different configurations, different stress loads, different joining methods. In 1936, he had even submitted a proposal for a modular military bridge. The War Office had filed it away and forgotten about it. But Bailey hadn't stopped working on the problem. For 5 years, in the evenings after work, he had continued refining his design. The breakthrough came from a simple observation. Every previous military bridge tried to be complete in itself. Engineers would build an entire bridge structure, then attempt to transport and install it as one piece. This required heavy equipment, careful handling, and substantial time. Bailey's insight was radical in its simplicity. Don't build a bridge. Build a bridge-building system. On February 14, 1941, Bailey received a letter from the War Office. His old proposal had been rediscovered. He was ordered to prepare a full-scale working prototype for testing in May. He had less than 3 months. Bailey didn't sleep much during those months. The prototype that emerged from Christchurch in May 1941 looked deceptively simple. Rectangular steel panels, each 10 feet long and 5 feet high. Crossbeams called transoms. Floorboards called stringers. Each component could be carried by 6 men. Each component could fit in a standard 3-ton military truck. Each component used standardized pin connections that required no special tools. The genius was in the modularity. Need a longer bridge? Add more panels. Need a stronger bridge? Stack the panels in multiple layers, creating triple-single, double-double, or triple-triple configurations. Need to cross a wider river? Add pontoons beneath the panels. The same components could create a bridge 20 feet long or 2,000 feet long. Could support 10-ton trucks or 60-ton tanks. Could span dry gaps or flowing rivers. The May 1941 trials at Christchurch became legendary among British engineers. Bailey's bridge was tested against every existing design. The Inglis bridge required 4 hours to assemble with specialized equipment. Bailey's bridge was erected in 1 hour by regular infantry. The Callender-Hamilton bridge could carry 26 tons but required cranes. Bailey's bridge carried 40 tons using only hand tools. The engineers stress-tested Bailey's design to destruction. They loaded it with progressively heavier tanks. First a Matilda at 23 tons. The bridge held. Then a Churchill at 40 tons. The bridge held. Then they filled the Churchill's interior with scrap iron to add even more weight. The bridge held. When it finally failed, the load exceeded 70 tons, far beyond any military requirement. Field trials began immediately. By December 1941, the first production Bailey bridges were issued to Royal Engineer units. By July 1942, production had reached 25,000 panels per month. Over 650 British companies were manufacturing components, from major steel mills to small machine shops. The genius of Bailey's design was that the parts were simple enough for any competent manufacturer to produce, yet precise enough that components from different factories were completely interchangeable. A pin manufactured in Birmingham would fit perfectly with panels made in Coventry. Transoms from Glasgow worked seamlessly with stringers from London. This interchangeability would prove crucial when American factories began production. More importantly, it meant that damaged sections could be replaced without dismantling entire bridges. Engineers could carry spare panels forward and swap out damaged components under fire. The first combat test came on November 26, 1942. 237th Field Company Royal Engineers were advancing through Tunisia with Montgomery's 8th Army. They reached the Medjerda River near Medjez el Bab at nightfall. German forces had demolished the existing bridge. The river was 100 feet wide, running fast with winter rains. Montgomery's advance schedule called for tanks to cross by dawn. In peacetime, engineers would have spent days surveying the site, calculating loads, planning the construction. There was no time for that. The engineers had 12 hours. They worked through the night by lamplight, assembling panels on the western bank, then pushing the growing bridge structure across the river using rollers. German patrols probed the position. Artillery fire landed periodically along the riverbank. The engineers kept working. At dawn on November 27th, the first British tanks rolled across the completed bridge. Montgomery's offensive continued without delay. German commanders were stunned. Their intelligence had reported the bridge destroyed. According to their calculations, the British would be delayed at least 3 days, possibly a week. Instead, armour was already across and advancing by sunrise. How was this possible? The answer was being demonstrated at dozens of river crossings across North Africa. At Leonforte in Sicily, Canadian engineers built the first Bailey Bridge under direct enemy fire. German machine gunners had clear lines of sight to the construction site. Mortar rounds landed among the working parties. The engineers took casualties but kept assembling panels. The bridge was completed in 6 hours. German defenders abandoned their positions when they saw tanks crossing almost before the last panels were connected. By the end of the North African campaign in May 1943, British and American forces had built hundreds of Bailey bridges. German commanders began to understand they were facing something new. The Wehrmacht's standard defensive strategy relied on river barriers. German engineers were trained to thoroughly demolish bridges during retreats. They used massive amounts of explosives, often destroying not just the bridge spans but the supporting piers as well. The theory was sound. Without bridges, Allied armour would be stopped at every river, buying time for German forces to establish new defensive lines. The theory failed because of one crucial miscalculation. German engineers assumed Allied forces would need to rebuild permanent bridges. Traditional military bridges required extensive site preparation, specialized equipment, and significant construction time. A destroyed bridge should delay an advancing army for days or weeks. But Bailey bridges didn't need permanent piers. They didn't require extensive site preparation. They could be built by infantry with hand tools. Even more frustrating for German forces, Bailey bridges could utilize the rubble of demolished bridges. Those stone piers the Germans left standing, perfect support points for Bailey panels. Those concrete abutments? Excellent anchor points. The more thoroughly the Germans demolished their bridges, the more material they left behind that Allied engineers could incorporate into new structures. Destruction became construction material. The United States Army officially adopted the Bailey Bridge system in early 1942, designating it the Portable Panel Bridge. American production began with contracts to Detroit Steel Products Company, American Elevator Company, and Commercial Shearing and Stamping Company. By mid-1943, American factories were producing 20,000 panels monthly. The standardization that made British production work created an unexpected challenge. American manufacturers, working from British specifications, discovered that different factories had slightly different interpretations of tolerances. The problem emerged in North Africa. An American engineer unit tried to use panels from two different manufacturers. The pins didn't quite fit. The holes were off by fractions of an inch. Eventually, 850 American-manufactured bridge sets had to be tracked down and marked as standalone systems, incompatible with other sets. It was an embarrassing discovery that highlighted the precision required for true interchangeability. British manufacturers, with more experience in quality control for military specifications, had maintained consistency across hundreds of factories. American production eventually matched this precision, but the learning process took months. The Sicily campaign in July 1943 demonstrated both the power of the Bailey system and the desperation of German defensive efforts. As Patton's forces drove toward Messina, German engineers demolished every bridge along the coastal highways. The demolitions were thorough and professional. Bridges were destroyed at their weakest points. Approach roads were mined. Riverbanks were pre-registered for artillery fire. American engineers responded by building Bailey bridges at a pace that shocked German observers. A bridge destroyed at dawn would carry traffic by sunset. In one remarkable instance near Randazzo, engineers discovered that German forces had destroyed a bridge so completely that even the piers were gone. They simply built a longer Bailey span, stretching the bridge from one intact section of approach road to the other, bypassing the destroyed section entirely. The bridge was in operation 24 hours after American forces reached the site. 3rd Infantry Division engineers rebuilt 37 demolished bridges during the Sicily campaign. The average construction time was 8 hours. This included sites where German forces had destroyed not just bridges, but entire sections of mountain roads carved from cliffsides. In those cases, engineers built Bailey bridges spanning the gaps where roads had been. Tanks that should have been stopped for days were rolling forward before German headquarters even received reports of the original demolitions. The Italian campaign, beginning in September 1943, became a marathon test of Allied engineering versus German demolition. Italy's geography favoured defence. Rivers ran perpendicular to the Allied line of advance. Mountains channeled movement into narrow valleys. German forces under Field Marshal Albert Kesselring executed a textbook fighting withdrawal, making maximum use of terrain and demolitions. Kesselring's strategy was brilliant in concept. German forces would establish strong defensive positions behind major rivers. They would delay Allied advances long enough to fully prepare the next defensive line. When pressure became too great, they would conduct organized withdrawals, destroying every bridge, mining every road, and demolishing every structure that could provide shelter. Each river should buy at least a week of time. The Volturno River north of Naples was the first major test of this strategy. German engineers destroyed 11 bridges along a 30-mile front. They demolished approach roads. They flooded low-lying areas. They created what appeared to be an impenetrable barrier. British and American forces reached the river on September 30th. By October 2nd, 7 Bailey bridges were operational. German defensive plans that assumed a few weeks' delay collapsed in 48 hours. The pattern repeated at the Trigno River, the Sangro River, the Moro River, the Garigliano River. Each river represented days or weeks of German preparation. Each demolition was thorough and professional. Each delay lasted hours instead of days. At the Sangro River, German forces destroyed 19 steel spans, but left 14 stone piers intact. British engineers used those piers to support Bailey bridges. What should have been a multi-week construction project was completed in 4 days. The psychological impact on German soldiers was profound. Corporal Hans Müller, serving with the 15th Panzer Grenadier Division, wrote in a letter captured by Allied intelligence, "Our engineers tell us they have bought us 3 days. We dig our positions. We prepare our defences. We watch the river. The next morning, American tanks are crossing on bridges that appeared overnight. How do they do this? Our commanders say it is impossible. But we see it with our eyes. They build bridges faster than we can destroy them. What is the point of defence if every river is crossed before we can prepare the next line?" This erosion of confidence in defensive capabilities affected German morale throughout the Italian campaign. Soldiers stopped believing that rivers would protect them. They stopped trusting that demolitions would buy them time. When defensive plans consistently failed to provide the promised delays, faith in leadership deteriorated. The Winter Line, officially the Gustav Line, represented Kesselring's most ambitious defensive effort. Anchored on the monastery at Monte Cassino, the line exploited rivers, mountains, and prepared fortifications. German engineers spent months preparing the positions. Every bridge for 20 miles in either direction was pre-wired for demolition. Every approach was covered by artillery. The defences were as strong as engineering could make them. The Gustav Line held longer than previous positions, but not because of demolished bridges. It held because of terrain, weather, and fierce German resistance. Allied engineers built Bailey bridges across the Rapido River, the Garigliano River, and numerous smaller streams. The bridges appeared as quickly as anywhere else in Italy. What slowed the Allied advance was mud, mountains, and German soldiers fighting from prepared positions, not destroyed infrastructure. The Rapido River crossing in January 1944 demonstrated both the horror of opposed river crossings and the determination of combat engineers. The 36th Infantry Division attempted to cross the Rapido in assault boats, establish a bridgehead, then allow engineers to build Bailey bridges for armour support. German defences were formidable. Pre-registered artillery covered every foot of the riverbank. Machine guns had interlocking fields of fire. The river itself was fast, cold, and difficult to cross. The infantry assault became a catastrophe. Boats were hit by artillery before reaching the water. Those that launched were swept downstream by current or riddled by machine gun fire. Engineers trying to build footbridges worked under continuous fire. 4 footbridges were planned. Only 1 was completed before being destroyed. The attack failed with nearly 1,700 casualties. But even in this failure, engineers demonstrated extraordinary courage. Technical Sergeant Anthony D'Amato led a bridge-building crew under direct fire. His official citation, preserved in National Archives, describes the action. Sergeant D'Amato led his squad to the riverbank at 2,200 hours. Despite heavy artillery and machine gun fire, the squad began assembling a footbridge. 3 men were killed in the first 10 minutes. Sergeant D'Amato continued directing construction. At 2,340 hours, artillery fire destroyed the partially completed bridge. Sergeant D'Amato immediately began constructing a second bridge at a different location. At 0130 hours, this bridge was completed. Infantry elements crossed until 0300 hours when enemy fire destroyed the bridge. Sergeant D'Amato's actions enabled over 200 infantry soldiers to cross and establish positions on the far bank. D'Amato survived the Rapido crossing, but was killed 2 months later while building a bridge at Anzio. His story exemplified thousands of similar stories of engineer courage throughout the Italian campaign. They built bridges knowing they were under observation. They worked knowing artillery could land at any moment. They continued after casualties because soldiers needed bridges more than engineers needed safety. When the Gustav Line finally broke in May 1944, it broke not because bridges were built faster, but because overwhelming Allied firepower and determination eventually overcame German defences. But once the line broke, Bailey bridges enabled rapid exploitation. Within days of the breakthrough, Allied armour was racing toward Rome. German forces attempted to establish new defensive positions at each river, but Bailey bridges appeared faster than defensive lines could form. The capture of Rome on June 4, 1944 showcased Allied engineering capability on a grand scale. As German forces retreated north, they demolished every bridge in and around Rome. The Tiber River alone had 14 major bridges, all destroyed. Allied engineers built Bailey crossings within hours. By June 6, when world attention shifted to the Normandy invasion, Rome's bridges were already being restored, and Allied forces were pursuing retreating German armies northward. The Gothic line, stretching across northern Italy from La Spezia on the west coast to Pesaro on the east coast, represented Germany's final major defensive position in Italy. Kesselring's engineers transformed the area into a fortress. They built bunkers, laid minefields, created anti-tank obstacles, and prepared every bridge for demolition. The defensive preparations took months and employed Italian forced labour along with German engineers. When Allied forces reached the Gothic line in August 1944, German forces demolished hundreds of bridges. Every stream, every river, every ravine lost its crossings. This should have stopped or severely delayed the Allied advance. Instead, engineer battalions built over 700 Bailey bridges along the Gothic line in 6 months. Major Harold Stevens commanded an engineer battalion assigned to support the attack on the Gothic line. His after-action report provides statistics on their operations. Between August 15th and November 30th, 1944, this battalion built 93 Bailey bridges, ranging from 40 feet to 300 feet in length. Average construction time was 6.2 hours. Longest construction time was 14 hours for a 300-foot span across the Reno River. Shortest time was 2.1 hours for a 40-foot span across the Idis River. Battalion operated under enemy fire during 72 bridge construction operations. Battalion casualties during this period: 18 killed, 53 wounded. No bridge construction operation was abandoned or delayed beyond scheduled completion due to enemy action or casualties. These statistics, dry and factual, conceal human drama behind every number. 18 men killed meant 18 families receiving telegrams. 53 wounded meant 53 soldiers enduring pain, fear, and uncertain recovery. Yet the bridges kept getting built because that's what engineers did. The German retreat through Italy demonstrated the futility of their demolition strategy. At every river they destroyed bridges. At every river, Bailey bridges appeared. German rear guards would report bridges demolished, defensive positions prepared, delays achieved. Then reports would arrive of Allied armour crossing rivers on Bailey bridges, defensive positions being bypassed, rear guards in danger of encirclement. Oberleutnant Karl Schmidt, commanding a rearguard company, wrote in his diary, "We retreated across the Santerno River on November 8th. Our engineers detonated the bridge after we crossed. I watched the bridge collapse into the river. Beautiful demolition work. We established defensive positions on high ground overlooking the crossing site. Our orders were to hold for 48 hours while the division established the next defensive line. At dawn on November 9th, we saw American engineers beginning bridge construction. By noon, their bridge was complete. By 1400 hours, tanks were crossing. We received orders to retreat immediately or be cut off. We held our position less than 30 hours instead of 48. This pattern repeats at every river. Our engineers demolish perfectly. Enemy engineers rebuild faster than we can retreat. This compression of defensive timelines forced German forces into increasingly desperate situations. The defensive doctrine assumed time to prepare each position. Bailey bridges eliminated that time. German forces arrived at the next river exhausted from constant retreat. They had hours instead of days to prepare defences. Their morale deteriorated as defensive position after defensive position proved untenable. The Allied advance up the Italian peninsula, measured in months and costing thousands of casualties, would have taken years without Bailey bridges. Every river would have required opposed crossings in assault boats, followed by days or weeks of bridge construction before armour could advance. German forces would have had time to prepare strong defensive positions at each line. The Italian campaign, already grinding and costly, would have been catastrophic, without rapidly deployable bridges. By the end of the war, The US Fifth Army and British Eighth Army had built over 3,000 Bailey bridges in Sicily and Italy alone. The total length of bridging exceeded 55 miles. The average span was 100 feet. Some bridges were much longer. Each bridge represented a German demolition that failed to stop the Allied advance. The longest Bailey bridge in Italy spanned the Senio River at over 400 feet. Construction took 36 hours and required coordination between 2 engineer battalions. The bridge replaced a demolished railroad bridge that German forces had destroyed so completely that locals believed the crossing would remain impassable for years. Allied engineers rebuilt it in a day and a half. The most difficult Bailey Bridge construction in Italy occurred at the Foglia River. German forces had not only demolished the bridge but triggered landslides that blocked both approaches. The river ran through a deep gorge with steep banks. Site access was terrible. German artillery had the entire area targeted. Construction took 5 days, far longer than typical, but engineers persisted because the crossing was strategically critical for operations against the Gothic Line. Lieutenant Colonel James Bradford commanded the engineer unit assigned to the Foglia River Bridge. His memoir, published after the war, describes the challenges. We couldn't bring trucks to the normal assembly area because of the landslides. We had to carry panels by hand down steep slopes. Each panel required 6 men and careful footing. One slip meant 6 men tumbling down a cliff face with a 500-pound steel panel. We lost 4 men to falls before we developed better techniques. German artillery fire was constant. We worked in short bursts between bombardments. When shells landed, everyone would take cover, then resume work immediately after. The gorge walls provided some protection, but the bridge site itself was completely exposed. We built in sections, finishing each segment before German fire could destroy too much work. It took 5 days of hell, but we finished. Armour crossed within hours. All that German demolition work, all that natural defensive terrain, overcome by determination and Bailey panels. The French campaign following the Normandy invasion in June 1944 showcased Bailey bridges on an even larger scale. The rapid Allied advance across France required crossing the Seine, the Loire, the Meuse, the Moselle, and dozens of smaller rivers. German forces demolished every crossing. Allied engineers built Bailey bridges at a pace that amazed even veteran observers. The Seine crossing in August 1944 involved building multiple Bailey bridges simultaneously. As Patton's Third Army raced eastward, engineers leapfrogged ahead, building bridges before armour arrived. In one remarkable 24-hour period, Third Army engineers built 9 Bailey bridges across various Seine tributaries. The average construction time was under 4 hours per bridge. Captain William Henderson supervised 4 of those bridges. He later wrote, "We had become so efficient that building Bailey bridges was almost routine. My company could build a 100-foot span in under 3 hours if conditions were good. We'd done it so many times that everyone knew their role perfectly. The trucks would arrive with panels. Teams would unload while other teams were already assembling. We'd have rollers positioned, pins ready, transoms staged. The bridge would grow across the gap like it was alive. Officers barely needed to give orders. Everyone knew what to do. We'd finish one bridge, convoy would move to the next site, and we'd start again. In 24 hours, we built 4 bridges totaling over 400 feet. Didn't seem extraordinary at the time. That's just what we did. This efficiency resulted from months of practice and dozens of bridges built under fire. By late 1944, veteran engineer units could build Bailey bridges faster than original designers had thought possible. The training, experience, and refined procedures created capability that exceeded theoretical limits. The adaptability of Bailey bridges extended to unusual situations. In the Netherlands, engineers built Bailey bridges with height-adjustable supports to accommodate tidal variations. The bridges needed to function at high tide and low tide, requiring support structures that could compensate for water level changes of over 10 feet. Engineers developed jackscrew systems that allowed height adjustment without disassembling the bridge. In the Huertgen forest, engineers built Bailey bridges through dense woodlands where normal bridge sites didn't exist. They cleared minimal approaches, built short spans across small streams, and created a network of bridges that enabled armour movement through terrain the Germans considered impassable for tanks. These short bridges, some only 30 or 40 feet long, proved as important as major river crossings because they opened new avenues of advance. One creative application involved using Bailey panels as temporary runways for small aircraft. In several instances, engineers laid Bailey panels across soft ground to create improvised landing strips. The panels distributed aircraft weight sufficiently to prevent the planes from sinking into mud. While not their intended purpose, the panels' load-bearing capacity and modular design made them suitable for emergency airfield construction. Technical Sergeant Arthur Wilson participated in one such runway construction. We got orders to build a landing strip for L-4 observation aircraft. Ground was too soft for normal operations. Someone suggested using Bailey panels. We laid them out like a roadway, bolted them together, and had a runway in 3 hours. The planes landed fine. Panels held the weight perfectly. After the war, I learnt that engineers in other theatres had done the same thing independently. The Bailey system was so flexible that creative uses emerged whenever engineers faced unusual problems. The statistics of Bailey Bridge construction during World War II reveal the scale of the revolution. British and American forces built over 700,000 panels worth of Bailey bridging, equivalent to over 444,000 metric tons of equipment. Over 650 British companies manufactured components. American production involved dozens of companies across multiple states. In Northwest Europe alone, from June 1944 to May 1945, American and British engineers built over 2,000 Bailey bridges. That's an average of 9 bridges per day for 11 months of continuous operations. Some days saw dozens of bridges built simultaneously across the front. Other days saw only a few, but the average held steady, demonstrating sustained capability over extended operations. Individual bridges demonstrated extraordinary capability. The longest floating Bailey bridge exceeded 1,000 feet, built by British engineers across the Rhine north of Wesel. Construction required coordinating multiple engineer battalions and took 2 days despite calm conditions, simply because of the bridge's length. Once completed, it could handle constant traffic, including 60-ton tank transporters. The highest Bailey bridge was built in Burma at an elevation of over 6,000 feet. Engineers worked in thin air with reduced physical capacity, while dealing with steep terrain and limited site access. The bridge spanned a mountain gorge and remained operational throughout the Burma campaign, supporting the drive to liberate Burma from Japanese occupation. The quickest Bailey Bridge assembly was completed in under 1 hour by a veteran engineer company in France. The bridge was only 70 feet long, and conditions were ideal. No enemy fire, good weather, flat approaches, and a crew that had built hundreds of bridges. They assembled it as a demonstration for visiting commanders, showing what perfectly trained engineers could accomplish with optimal conditions. The longest continuous service for a single Bailey bridge occurred in Italy, where a bridge built in November 1943 remained operational until July 1946. The bridge was maintained, repaired, and occasionally modified, but its basic structure remained unchanged for nearly 3 years. This longevity demonstrated that while Bailey bridges were designed as temporary structures, they could serve indefinitely with proper maintenance. The statistics tell a broader story. Third Army in France employed nearly 27,000 feet of Bailey bridging of varying lengths. In Northwest Europe, from June 1944 to May 1945, American and British engineers built over 2,000 Bailey bridges. That's an average of 9 bridges per day for 11 months of continuous operations. Each bridge had a story. Captain James Morrison, commanding an engineer company with the 4th Infantry Division in France, described a typical situation. We reached the Moselle on September 5th. The bridge was destroyed, just twisted steel and broken concrete in the river. Division wanted tanks across by dawn. We had 10 hours. The company assembled at the riverbank at 8 p.m. We worked in shifts, 20 men building while 20 rested. German artillery hit us periodically. We lost 3 men killed, 7 wounded, but we kept building. By 5:30 a.m., the bridge was done. First tank crossed at 6:15. We were asleep by 7. At noon, orders came to move to the next river. The Germans had just blown that bridge too. This became the rhythm of advance. Reach a destroyed bridge. Build a Bailey crossing. Move armor forward. Sleep if there's time. Move to the next destroyed bridge. The cycle repeated dozens, then hundreds of times. Engineers built bridges so routinely that it became background noise in the larger campaign. German attempts to destroy completed Bailey bridges proved equally futile. Artillery fire could damage panels, but engineers simply replaced them. The modular design meant a damaged section could be swapped out in minutes. Luftwaffe bombing runs achieved temporary delays but couldn't permanently close crossings. Engineers kept spare panel sets near every major bridge. Even direct hits rarely destroyed enough sections to close a bridge for more than a few hours. Technical Sergeant Robert Chen, an engineer with the 29th Infantry Division, explained the repair process. Whenever Germans hit one of our bridges, we'd assess the damage. Usually they'd destroy 2 or 3 panels. We'd pull up with a truck carrying spares. 6 of us would unbolt the damaged section, drop it in the river, and bolt in new panels. Whole process took maybe 30 minutes if we worked fast. Then the bridge was good as new. The Germans would waste ammunition hitting the same bridge over and over. We'd repair it every time. The modular nature of the Bailey system meant that damage was rarely catastrophic. Unlike traditional bridges where structural damage to one section could compromise the entire span, Bailey bridges could lose entire panels and remain functional. Engineers would simply redirect traffic to undamaged lanes or quickly replace destroyed sections. This resilience was built into the design philosophy from the beginning. Bailey himself had understood that combat bridges would face constant attack. His solution wasn't to make bridges indestructible. That was impossible. Instead, he made them rapidly repairable. Every component was designed to be removed and replaced quickly. The pin connections that seemed so simple were actually precisely engineered to allow fast assembly and disassembly under stress. This approach reflected a fundamental shift in military engineering thinking. Traditional engineers tried to build structures strong enough to resist all damage. Bailey recognized that in combat, everything eventually gets damaged. The question wasn't whether the bridges would be hit, but how quickly they could be repaired. By making repairs trivial, he made the bridges effectively indestructible in operational terms. The German experience with Bailey bridge resilience became increasingly frustrating as the war progressed. Artillery units would receive coordinates for bridge sites. They would fire scheduled bombardments, expending hundreds of shells. Observers would report successful hits, panels destroyed, bridges damaged. Within hours, reconnaissance would report the same bridges operational again. German gunners began to feel their efforts were pointless. Lieutenant Friedrich Steiner, serving with an artillery battalion in Italy, recorded his frustration in a diary later captured. "We have fired on the American bridge at the Volturno crossing for 3 days. We have scored multiple direct hits. We have destroyed sections of the structure. Yet every morning the bridge stands, trucks cross, tanks cross. It is as if we are shooting at ghosts. Our ammunition expenditure is enormous. Our effect is negligible. The Americans repair damage faster than we can create it." This asymmetry in the damage versus repair equation gave Allied forces an enormous advantage. German forces had to expend significant resources trying to destroy bridges. Allied engineers needed only modest resources to repair them. Over time, this imbalance drained German capabilities while barely affecting Allied operations. The psychological warfare value of Bailey bridges was substantial. German soldiers watched their engineers work for hours, sometimes days, preparing thorough bridge demolitions. The explosions were impressive. The destruction appeared total. Then, Allied forces would arrive and have bridges operational within hours. This demonstration of Allied capability and German futility damaged morale more effectively than propaganda ever could. Staff Sergeant William Kowalski, an intelligence officer with the 1st Infantry Division, described interrogating German prisoners. "We'd ask them about morale, about supplies, about their officers, but they kept coming back to the bridges. They couldn't understand how we built them so fast. Some thought we had secret technology. Others believed we had massive numbers of engineers. A few thought it was magic. They just couldn't accept that simple design and good training made the difference. Their whole concept of warfare assumed destroyed bridges meant delays. We demolished that assumption along with their defensive strategy. This resilience drove German commanders to distraction. They couldn't predict where Bailey bridges would appear because they could appear anywhere. A river crossing that looked impossible because of width or depth or current would suddenly have a bridge. An approach road destroyed by demolitions would be bypassed by a Bailey span. A defensive position protected by a river barrier would be outflanked by a bridge built overnight at an unexpected location. The Germans tried various countermeasures, all unsuccessful. They attempted to destroy bridge components in storage or transit. Allied logistics proved too robust. Trucks carrying panels travelled in protected convoys. Storage areas were dispersed and defended. Even when Germans succeeded in destroying stockpiles, replacement panels arrived quickly. They tried mining likely bridge sites. Engineers cleared the mines before beginning construction. The mine-clearing process sometimes took longer than building the bridge itself. They tried booby-trapping demolished bridges, hoping to kill engineers during initial surveys. Allied engineers developed protocols for checking demolished structures before approaching them. They even tried chemical agents on a few occasions, hoping to contaminate areas and prevent construction. This violated international law and proved ineffective anyway. Engineers wore protective equipment and built bridges in contaminated areas when necessary. The most sophisticated German countermeasure involved underwater obstacles. In some rivers, they sank obstacles on the riverbed, hoping to damage Bailey bridges supported by pontoons. Engineers simply adjusted pontoon placement or used pile-driving equipment to secure foundations. The obstacles became nuisances rather than barriers. German attempts to capture Bailey bridge equipment also failed. The components had no value without the knowledge of how to use them. A few times, German forces overran Allied engineer units and captured Bailey panels. They couldn't effectively deploy them. The simplicity that made Bailey bridges easy for trained Allied engineers to assemble didn't translate to untrained German forces working without documentation. Hauptmann Werner Koch, a German engineer officer, wrote in an after-action report, "We captured approximately 20 panels of the enemy's bridge system during our counter-offensive in the Ardennes. Our engineers examined them carefully. The components are well made but unremarkable. Steel panels with holes, simple pins, basic crossbeams. Yet somehow the Americans and British used these simple parts to build bridges with extraordinary speed. We attempted to assemble the panels using the captured components. Without proper training and documentation, the process is slow and uncertain. The American system's power lies not in the components themselves but in the training, logistics and doctrine that support their use." This observation highlighted a crucial truth. The Bailey Bridge system's effectiveness came from the entire ecosystem surrounding it, not just the hardware. The training that taught engineers to build quickly under fire, the logistics that delivered components to forward positions, the doctrine that emphasized rapid bridging as essential to maintaining offensive momentum, the industrial capacity that produced panels faster than they could be consumed, the quality control that ensured interchangeability. All these factors combined to create a capability greater than the sum of its parts. The contrast with German bridge systems was stark. German military bridges were technically sophisticated. The Wehrmacht employed several bridging systems, including the Brückenger et B and various pontoon bridges. These were well-engineered and capable systems, but they required specialized training, significant setup time, and careful handling. They couldn't be built under fire by regular infantry. They couldn't be repaired quickly when damaged. They couldn't adapt easily to unexpected situations. German doctrine emphasized thorough preparation and methodical execution. This worked well in offensive operations when German forces controlled the timing and location of river crossings. It failed catastrophically in defensive situations when rapid bridging would have enabled quick repositioning or counterattacks. By the time German engineers could establish a bridge, the tactical situation had usually changed. The philosophical difference between German and Allied approaches reflected broader differences in military culture. German engineering emphasized precision, sophistication, and technical excellence. Allied engineering emphasized adaptability, speed, and good enough solutions deployed quickly. In the fluid circumstances of World War II combat, the Allied approach proved superior. This doesn't mean German engineers were incompetent or German equipment was inferior. German engineers were highly skilled professionals. German bridge systems were technical achievements. But the Bailey Bridge system represented a better fit for the specific requirements of mobile warfare. The match between tool and mission was more important than any inherent technical superiority. The Battle of the Bulge in December 1944 demonstrated the system's flexibility in crisis. When German forces broke through American lines in the Ardennes, they captured or destroyed multiple bridges. As American forces counterattacked, engineers built Bailey bridges to restore supply lines. The conditions were brutal. Sub-zero temperatures froze fingers within minutes. Snow and ice made every surface treacherous. German artillery targeted every crossing site. Luftwaffe fighters strafed construction crews. Engineers worked anyway, because the surrounded forces at Bastogne needed supplies and the counter-offensive needed bridges. Captain Michael Sullivan commanded an engineer company assigned to build a bridge across the Arthur River. His after-action report, preserved in the National Archives, describes the conditions. Temperature was -15 degrees Fahrenheit. Wind chill made it feel like -30. My men worked in shifts, 30 minutes on, 30 minutes warming by fires. We lost 2 men to frostbite severe enough for evacuation. 3 were wounded by artillery fire, but we completed the bridge in 14 hours, 6 hours ahead of schedule. The alternative was leaving a tank battalion without supply for another day. We didn't have that day to spare. At Bastogne itself, 3 Bailey bridges maintained the corridor into the besieged town. German forces attacked these bridges relentlessly, understanding their strategic importance. Artillery fire was constant. German infantry probed the positions nightly. Engineers defended their bridges with rifles while keeping them operational. When shells damaged sections, repairs happened under fire. When snow drifted across approaches, engineers cleared it while machine gun fire crackled overhead. Staff Sergeant James O'Brien, an engineer at one of the Bastogne bridges, described a typical night. Germans would hit us every few hours, artillery first, then sometimes infantry trying to get close enough to plant charges on the bridge. We had 50 caliber machine guns positioned to cover the structure. Between attacks, we'd repair damage and clear snow. I don't think I slept more than 2 hours any night. That's a week. We drank coffee until we ran out, then just stayed awake on adrenaline and determination. That bridge couldn't fail. Too many people depending on it. The Bastogne bridges held. Supplies flowed. The defenders held. The German offensive failed. Bailey bridges had proven themselves in the worst possible conditions, defensive warfare in winter against desperate attacks. If they could work there, they could work anywhere. The flexibility of the Bailey system extended beyond standard bridge configurations. Engineers developed creative solutions to unique problems. In the Netherlands, they built Bailey bridges with adjustable heights to accommodate tidal variations. In Burma, they constructed suspension Bailey bridges across deep gorges. In Italy, they created multi-level bridges with vehicle traffic on one level and fuel pipelines on another. One remarkable application occurred in France during the pursuit after the Normandy breakout. Engineers discovered that Bailey panels could be used as temporary roadway over soft ground. They laid panels directly on muddy fields, creating instant roads for tanks and trucks. This wasn't what the bridges were designed for, but the modular components adapted perfectly. Entire tank columns crossed terrain that should have been impassable, bypassing German defensive positions that relied on terrain restrictions. Another creative use emerged during river crossing operations. Engineers would build Bailey bridges on rollers or pontoons, then float or push the entire structure into position. This allowed construction to happen safely behind friendly lines, then deployment under fire happened quickly. The technique reduced casualties and construction time at contested crossings. Lieutenant Colonel David Morrison, commanding an engineer battalion, described the process. We'd assemble the bridge completely, maybe 200 feet back from the river. We'd put it on rollers. When we were ready to cross, we'd push the whole bridge forward. Took maybe 50 men pushing, plus a tank to help. The bridge would roll right across dry ground, then we'd launch it across the river. Germans couldn't believe what they were seeing. A complete bridge appearing in minutes. By the time they reacted, we had tanks crossing. This technique wasn't in any manual. Engineers developed it in the field through experimentation and necessity. The modular design that Bailey had created allowed for innovations he had never imagined. The system was flexible enough that skilled engineers could adapt it to solve problems Bailey had never encountered. The adaptability extended to environmental conditions. Bailey bridges functioned in desert heat, jungle humidity, Arctic cold, and everything between. The steel components could withstand temperature extremes that would disable more complex systems. The simple design had no vulnerable mechanical parts to fail in adverse conditions. In North Africa, temperatures exceeded 120 degrees Fahrenheit. Metal became too hot to touch with bare hands. Engineers worked in the relative cool of early morning and evening, building bridges during hours when temperatures dropped to merely unbearable. The bridges themselves functioned perfectly. Steel expanded in heat, but the design accommodated thermal expansion without structural failure. In Northern Europe during winter, temperatures dropped below zero. Metal became brittle. Grease froze. Engines wouldn't start. Bailey bridges kept functioning. Engineers heated bolts with torches when pins wouldn't seat in frozen conditions. They cleared ice from panel holes. They worked with frozen fingers that barely felt the tools. The bridges didn't care about temperature. The simple mechanical connections worked regardless of weather. In Burma and the Pacific, humidity rusted everything. Tropical downpours created flash floods. Insects ate wooden components. Bailey bridges adapted. Engineers treated wood with preservatives. They painted metal panels with rust-resistant coatings. They built higher to accommodate flood levels. The basic system remained effective even in the worst tropical conditions. This environmental versatility meant Bailey bridges could deploy globally. A battalion trained in England could build bridges in Africa, Italy, France, or Burma, using identical techniques and equipment. The global reach of Allied operations required standardized equipment that worked anywhere. Bailey bridges met that requirement perfectly. The production statistics behind Bailey bridge operations reveal industrial capability on a massive scale. British factories produced over 650,000 panels during the war. American factories added hundreds of thousands more. Each panel required precision manufacturing. Each panel needed to be identical to within fractions of an inch. The quality control required to maintain interchangeability across hundreds of factories in 2 countries was extraordinary. Small engineering firms that had never done military work learned to produce Bailey components. A company that normally made agricultural equipment would receive specifications for panels and retool production lines. Within months, they'd be producing components identical to those from established steel mills. The simplicity of design made this distributed production possible. The logistics of delivering components to forward units was equally impressive. A typical Bailey bridge required 40 panels for a modest crossing. Each panel weighed 570 pounds. Moving enough components for multiple bridges meant dedicating substantial transport capacity to engineering supplies. Allied logistics planners prioritized bridge components because they understood how critical rapid bridging was to maintaining offensive momentum. Truck convoys carried panels from factories to ports, then ships transported them across oceans. At destination ports, more trucks moved them to supply dumps near the front lines. Engineer units drew components as needed, often building bridges within hours of receiving materials. The entire supply chain, from factory floor to combat construction site, operated with remarkable efficiency. This logistics capability gave Allied forces an advantage independent of the bridge design itself. Even if German forces had captured Bailey bridge plans and attempted production, they lacked the industrial capacity and logistics infrastructure to match Allied deployment rates. By 1944, Allied industrial superiority was overwhelming. Bailey bridges were one manifestation of that superiority, but they required the full weight of Allied production and logistics to reach their potential. The true test of the Bailey system came on the banks of the Rhine, Germany's greatest river, its final natural barrier, its traditional defense against invasion from the west. 766 miles long, an average width of 1,300 feet, swift current, deep channel. The Rhine had protected central Germany since the Roman Empire. In March 1945, it was all that stood between Allied armies and the German heartland. German strategy was simple: destroy every bridge, force the Allies to mount opposed river crossings, the most difficult military operation. Make them pay in blood for every crossing. Hold the line long enough to negotiate a settlement or deploy wonder weapons. By early March 1945, of the 47 bridges originally spanning the Rhine, only 4 remained standing. Hitler's orders were explicit. Every remaining bridge must be destroyed before Allied forces reached it. The first Allied Rhine crossing came almost by accident. On March 7, 1945, Combat Command B of the 9th Armoured Division approached the town of Remagen, expecting to find the Ludendorff Bridge destroyed like all the others. Instead, they saw it still standing, damaged but intact. German engineers had wired it with 2,800 kilograms of explosives, but when they triggered the charges, only partial detonation occurred. The bridge survived. First Lieutenant Karl Timmermann led Company A, 27th Armoured Infantry Battalion in a desperate rush to secure the bridge before German forces could detonate backup charges. His men sprinted across under fire, dodging shell holes and damaged sections. Army engineers followed immediately, frantically cutting wires and removing remaining demolition charges, while German artillery pounded the structure. The bridge held long enough for American forces to establish a bridgehead on the eastern bank. But the Ludendorff Bridge was severely damaged. It could carry light traffic, but wouldn't support heavy armor. More critically, German forces launched desperate counterattacks to recapture or destroy it. Artillery fire was constant. Luftwaffe bombers, including the new jet-powered Arado 234 and Messerschmitt 262, struck repeatedly. This is where the Bailey Bridge system proved its ultimate value. Even as engineers worked to stabilize the damaged Ludendorff Bridge, additional engineer units were arriving with Bailey Bridge equipment. The 51st Engineer Combat Battalion, under Lieutenant Colonel Harvey Fraser, began constructing a heavy pontoon bridge 3.2 kilometers upstream. The 291st Engineer Combat Battalion started a treadway bridge downstream. Fraser's crew began at 4 p.m. on March 10th. The far shore was not yet secured. German artillery observers on the eastern heights had perfect visibility of the construction site. Shells began falling within minutes. The forward end of the pontoon bridge, where floating sections were being attached, became known as Suicide Point. The name was earned. At 1 p.m. on March 10th, a direct hit killed 1 engineer and wounded 5 more. German pilots strafed the bridge sites. Artillery fire was constant. 17 engineers were killed or wounded in a single barrage that destroyed 19 pontoon floats. The battalion executive officer was killed by a direct hit that wounded 19 others. Engineers working on the bridges were called fugitives from the law of averages. They kept working. 27 hours after starting construction, Fraser's battalion completed a 969-foot pontoon bridge. It was the first Allied tactical bridge across the Rhine since the Napoleonic era. The bridge opened to traffic at 11 p.m. on March 11th. When German forces finally destroyed the damaged Ludendorff Bridge on March 17th, 3 Bailey-type bridges were already operational. 2 more engineer battalions, the 298th and the 988th, completed a heavy-duty treadway bridge on March 11th. Total construction time: 32 hours under constant fire. The bridge was 1,032 feet long, capable of supporting 50-ton loads. It was the fastest Allied bridge built across a major river while under direct attack. But the Rhine crossings weren't finished. Field Marshal Bernard Montgomery was planning Operation Plunder, a massive 3-army assault across the Rhine north of the Ruhr. The operation was scheduled for March 23rd and would include 5,000 guns in the opening bombardment, massed airborne drops, and multiple river crossings. Montgomery's engineers had months to prepare, stockpiling enormous quantities of bridging equipment. General George Patton, commanding 3rd Army to the south, had different ideas. On the night of March 22nd, one day before Montgomery's carefully planned offensive, Patton sent the 11th Infantry Regiment, 5th Infantry Division across the Rhine at Nierstein. They used Duke W amphibious trucks and Navy landing craft. No artillery preparation, no airborne assault, no massive build-up. Just infantry crossing in darkness. By late afternoon on March 23rd, Patton's engineers had completed a 40-ton treadway bridge. 3rd Army was across the Rhine and expanding a bridgehead before Montgomery's artillery barrage even began. Patton made sure the press knew that 3rd Army had crossed without benefit of aerial bombing, ground smoke, artillery preparation, and airborne assistance. It was a calculated slight aimed at Montgomery's elaborate preparations. But Montgomery's engineers had their own moment of triumph. On the night of March 23rd, Companies E and C of the 17th Armoured Engineer Battalion constructed treadway rafts south of Wesel. Bridge construction started at 9:45 a.m. on March 24th. By 4 p.m., the first truck crossed the floating pontoon bridge. Over 1,152 feet of treadway and 93 pneumatic floats were laid in 6 hours and 15 minutes. It was a record for a bridge of that size. Within 2 weeks of the first Remagen crossing, 10 American divisions had crossed the Rhine. Multiple Bailey-type bridges were operational at Remagen, Nierstein, Boppard, Sankt Goar, Oberwesel, Worms, and Oppenheim. British and Canadian forces crossed at Wesel and Ries. In every case, bridges were operational within 24 hours of the initial crossing. German demolitions of the original Rhine bridges had accomplished nothing except providing practice for Allied engineers. The Germans finally understood what they were facing. General Oberst Alfred Jodl, chief of the operations staff of the Armed Forces High Command, wrote in a classified report, The American bridge-building capability has rendered our entire defensive doctrine obsolete. We calculate delays in days. They build bridges in hours. We destroy infrastructure they require. They carry their infrastructure with them in trucks. Our engineers train for months to build traditional bridges. Their infantry builds bridges as easily as they dig foxholes. This is not a technological advantage, it is a philosophical revolution in military engineering. The philosophy was indeed revolutionary. Traditional military bridges were engineering marvels, complex structures that demonstrated technical sophistication. Bailey bridges were the opposite. Each component was simple. A child could understand how the parts fit together. The pins that connected panels required no special tools, just a sledgehammer. The panels themselves were just steel rectangles with holes. The transoms were just crossbeams. The stringers were just floorboards. But this simplicity was deceptive. Each component had been designed with extraordinary precision. The load-bearing calculations were complex. The steel alloys were carefully selected. The welding patterns were specifically engineered to distribute stress. The dimensions were exact to within fractions of an inch. The simplicity that engineers saw when assembling bridges concealed the sophisticated engineering that had gone into designing the system. This combination of simple assembly and sophisticated design had profound implications. Because assembly was simple, regular infantry could build bridges with minimal training. Because components were light, they could be transported in ordinary trucks. Because the system was modular, engineers could adapt to any situation. Because parts were standardized, logistics were straightforward. Because fabrication was simple, production could be distributed among hundreds of factories. The impact on the German military was catastrophic. The Wehrmacht's doctrine assumed that rivers and demolitions would slow Allied advances by days or weeks. This assumption was built into every defensive plan, every withdrawal schedule, every logistics calculation. When Bailey bridges rendered that assumption false, the entire German defensive strategy unraveled. German forces would establish defensive positions along a river, confident that destroyed bridges would hold attackers for sufficient time to fortify the next line. Allied forces would reach the river at dawn, and German observers would report bridges destroyed as planned. By sunset, tanks would be crossing on Bailey bridges. German defenders would receive orders to hold for 3 more days to allow the next defensive line to prepare. But Allied armour would already be bypassing their positions, forcing immediate withdrawals. The psychological impact was devastating. German soldiers stopped believing in defensive lines. They stopped believing their engineers could buy them time. They stopped believing that demolitions would slow the Allied advance. This erosion of confidence contributed to the rapid collapse of German resistance in the final months of the war. Private First Class Robert Martinez, a combat engineer with the 51st Engineer Combat Battalion, described building the first pontoon bridge across the Rhine. We knew German artillery had the site ranged. Every few minutes, shells would land near the bridge. You'd hear the scream, hit the deck, wait for the explosion, then get back to work. We lost guys every shift. You'd be working next to someone, helping them position a panel, then there'd be an explosion and they'd be gone. But we kept building, because we knew if we stopped, soldiers on the other side would die. Tank crews were counting on us. Infantry was waiting for supplies. You can't stop building because you're scared. You stop being scared and you just build. The training that produced engineers capable of this level of performance under fire was comprehensive and realistic. Engineer battalions trained for months before deployment, practicing bridge construction until the process became automatic. Training emphasized speed, working in darkness, and operating under simulated combat conditions. Corporal Thomas Washington described his training in England before D-Day. We built Bailey bridges until we could do it blindfolded. Literally. Our officers would make us assemble bridges at night with no lights. We'd build in rain, in mud, in wind. We'd build while sergeants threw smoke grenades and fired blank ammunition to simulate combat. They'd shout that casualties had occurred, and we'd have to continue with reduced crews. By the time we went to France, building bridges wasn't a challenge, it was just what we did. This training intensity paid enormous dividends in combat. Engineers who had built dozens of practice bridges could work efficiently under actual fire. The muscle memory of assembly procedures meant they could continue working even when exhausted or terrified. The redundant crew structure meant bridge construction could continue despite casualties. The training also emphasized improvisation. Engineers learned to adapt to unexpected situations. If components were damaged, They learned to use available materials as substitutes. If site conditions differed from standard configurations, they learned to modify procedures. If equipment was lost or destroyed, they learned to accomplish tasks with whatever remained. Sergeant First Class Eugene Parker, an engineering instructor, explained his teaching philosophy. "I told my men that the enemy gets a vote. Your bridge site won't be perfect. Your equipment won't always be complete. Your time won't be adequate. Your support won't be guaranteed. You still have to build the bridge. So we train for worst-case scenarios. If you can build a bridge in the dark, in the rain, with half your crew missing equipment, you can handle whatever combat throws at you." This philosophy produced engineers capable of remarkable achievements under terrible conditions. The bridges built at Remagen, at Bastogne, at dozens of other critical sites, were built by men who had been trained to succeed regardless of circumstances. Their determination, their skill, their courage made the Bailey system effective. The human cost of combat, bridging, was significant. Engineers were high-value targets. German forces understood that destroyed bridges created delays, but destroyed engineers created longer delays. Artillery observers prioritized bridge sites. Snipers targeted officers and NCOs directing construction. Luftwaffe pilots strafed engineer units whenever possible. Engineer casualties throughout the European theatre were proportionally higher than infantry casualties in many sectors. Engineers worked in exposed positions, often with limited overhead cover. They couldn't dig foxholes while assembling bridges. They couldn't take cover during artillery bombardments without abandoning their work. They built bridges because soldiers needed bridges, accepting risks that would have seemed suicidal in other contexts. The collapse of the Ludendorff Bridge at Remagen on March 17th killed 28 engineers and injured 93 more. These men died or were wounded while working to repair and strengthen a bridge they knew was damaged and dangerous. They worked anyway because the strategic situation required it. Their sacrifice exemplified the dedication of combat engineers throughout the war. Sergeant Robert Billingsley survived the Remagen collapse. He described the moment. "We were working on the bridge deck, reinforcing weak sections. There was a sound, like metal tearing. Then the whole structure shifted. I grabbed for a support beam, but it was moving too. The bridge just folded up and fell. I went into the water. The current was strong and cold. I managed to grab onto a piece of debris. Other guys weren't so lucky. Some were trapped in the wreckage. Some were swept away. I got pulled out downstream by a boat crew. When they counted casualties, half our platoon was gone. But we were back, building the next bridge the following day. That's what engineers did. This resilience and determination characterized engineer units throughout the war. They took casualties and kept building. They endured terrible conditions and kept building. They faced situations that seemed impossible and kept building. The Bailey Bridge system gave them the tools to succeed, but their courage and skill made success reality. The contribution of combat engineers to Allied victory was profound but often overlooked. Infantry got the glory of capturing objectives. Armor got the credit for breakthrough operations. Artillery received recognition for fire support. Engineers quietly built the infrastructure that made all other operations possible. Without their bridges, infantry couldn't advance. Without their roads, armor couldn't maneuver. Without their support, artillery couldn't displace forward. Field commanders understood this. General Eisenhower stated in his memoirs that he never worried about river crossings because he knew his engineers would build bridges. General Patton, known for his love of aggressive armored warfare, repeatedly credited engineers with enabling Third Army's rapid advances. General Bradley specifically cited Bailey Bridges as one of the key capabilities that made victory possible. That determination defined the engineer units throughout the war. At the Rapido River in Italy, engineers built footbridges under direct machine gun fire. In Sicily, they cleared mines while constructing bridges. In France, they worked through winter storms. In Germany, they built under Luftwaffe attack. The Bailey Bridge was only as good as the men who assembled it. The bridges they built changed the war's outcome. Without Bailey Bridges, the Italian campaign would have stalled at every river. Without Bailey Bridges, the advance from Normandy would have taken months longer. Without Bailey Bridges, the Rhine crossing would have been far more costly. Every bridge built under fire bought time for infantry advancing under fire. Every span completed ahead of schedule saved lives. German attempts to counter the Bailey Bridge system failed completely. They tried heavier demolitions, using more explosives to destroy bridges and their approaches more thoroughly. This only created more rubble that Allied engineers incorporated into new construction. They tried focusing artillery on known bridge sites, pre-registering coordinates for intense bombardment. Engineers built at different locations or simply accepted casualties and kept working. They tried aerial bombardment of bridges and supply columns. Allied anti-aircraft defenses and fighter cover limited these attacks. The fundamental problem was that Bailey bridges could be built faster than German forces could destroy them. Even if Luftwaffe bombers destroyed a completed bridge, engineers rebuilt it within hours. Even if artillery destroyed stockpiled panels, more trucks arrived with replacements. The system was designed for resilience. Individual bridges could be destroyed, but the bridge-building capability couldn't be stopped. By April 1945, German resistance in the West was collapsing. The speed of the final Allied advance was enabled by Bailey bridges. When General Bradley's 12th Army Group and General Dever's 6th Army Group advanced through southern Germany, they crossed dozens of rivers in weeks. Every crossing had multiple bridges operational within hours. The statistics of Bailey bridge construction during World War II reveal the scale of the revolution. British and American forces built over 700,000 panels worth of Bailey bridging, equivalent to over 444,000 metric tons of equipment. Over 650 British companies manufactured components. American production involved 32 companies across 28 states. The bridges appeared on every front where Allied forces fought: North Africa, Sicily, Italy, France, Germany, Burma, the Pacific Islands. Individual bridges demonstrated extraordinary capability. The longest floating Bailey bridge exceeded 1,000 feet. The highest span was built in Burma at an elevation of 6,000 feet. The strongest configuration could support 120 tons. The quickest assembly time was under 1 hour for a 70-foot span. The bridges served purposes beyond simply crossing rivers. Engineers used Bailey panels to create elevated roadways across swamps. They built temporary piers for landing ships. They constructed bridges to bypass destroyed sections of highways. They created emergency railroad crossings. They built supply routes across terrain that should have been impassable. Every impossible situation found a Bailey bridge solution. This adaptability drove German forces to distraction. They couldn't predict where Bailey bridges would appear because they could appear anywhere. A river crossing that looked impossible because of width or depth or current would suddenly have a bridge. An approach road destroyed by demolitions would be bypassed by a Bailey span. A defensive position protected by a river barrier would be outflanked by a bridge built overnight at an unexpected location. Field Marshal Montgomery stated that without the Bailey Bridge, we should not have won the war. This was not hyperbole. The Allied advance from Normandy to Berlin required crossing hundreds of rivers. German forces demolished thousands of bridges. Without a portable, rapidly deployable bridging system, each crossing would have required days or weeks of preparation. The war would have lasted months or years longer. The success of the Bailey Bridge influenced military engineering doctrine for decades. The principle of modular, portable, rapidly deployable equipment became standard. Modern military bridges, from the medium girder bridge to the improved ribbon bridge to the joint assault bridge, all trace their lineage to Bailey's innovation. The focus shifted from building permanent structures to creating flexible systems that could adapt to any situation. Post-war, Bailey bridges found extensive civilian use. War surplus bridges were sold to governments worldwide. They appeared in remote regions, spanning rivers and gorges where permanent bridges were impractical. After earthquakes, floods, or other disasters, Bailey bridges provided emergency crossings. In developing nations, they became semi-permanent infrastructure, serving communities for decades. The bridge Donald Bailey designed for military use in 1941 remains in production today. The civilian applications demonstrated the design's versatility beyond military requirements. In the 1950s and 60s, Bailey bridges appeared in Africa, Asia, and South America. Mining companies used them to access remote sites. Logging operations employed them for temporary access roads. Rural communities installed them as permanent replacements for destroyed or inadequate bridges. In India, the government purchased hundreds of Bailey bridges for rural development. These bridges connected isolated villages to regional road networks, transforming local economies. Rice paddies that had been inaccessible except by foot could suddenly receive trucks. Markets that had been distant and difficult became accessible. The economic impact of these bridges exceeded their military value, demonstrating how military technology could serve peacetime development. In Central America, Bailey bridges helped rebuild infrastructure after hurricanes and earthquakes. Traditional bridge construction took years and required specialized engineers. Bailey bridges could be installed in weeks using local labor with minimal training. The combination of speed, low cost, and adequate capability made them ideal for disaster response. Several Bailey bridges installed as temporary emergency crossings remained in service decades later, never replaced because they continued functioning adequately. The longest-lived civilian Bailey Bridge operated in Tasmania, Australia. Installed in 1945 to replace a wooden bridge destroyed by flood, the Bailey Bridge served continuously until 2003, when it was finally replaced by a modern concrete structure. 58 years of continuous service for a bridge designed as a temporary military expedient demonstrated remarkable durability. In 2018, the Indian Army installed new Bailey bridges in Mumbai to relieve crowding at commuter railway stations. These bridges, based on the 1941 design with modern materials, were erected in days and immediately began serving thousands of pedestrians daily. The incident occurred 77 years after Bailey's original design, yet the fundamental principles remained unchanged and effective. The design influenced civilian bridge engineering beyond just Bailey bridges themselves. The modular approach, the emphasis on standardized components, the focus on ease of assembly, all these principles informed modern bridge design. Contemporary modular bridge systems, whether for military or civilian use, owe intellectual debts to Bailey's innovations. Military applications continued evolving. The British Army developed the medium girder bridge in the 1970s as a Bailey successor. The design incorporated aluminum components for lighter weight and improved materials for greater strength, but the fundamental philosophy remained Baileysian. Modular components, simple assembly, maximum flexibility. The MGR served British forces for decades and continues in service with multiple militaries worldwide. The American M2 Bailey Bridge, developed in the 1960s, modernized the original design with updated materials and improved connections. These bridges deployed to Vietnam, served in Desert Storm, and continued seeing service in Iraq and Afghanistan. Each generation of military engineers learned bridge building using Bailey principles, even when specific equipment changed. The U.S. Army's current improved ribbon bridge system uses a completely different approach, employing inflatable pontoons and folding bridges, yet the doctrine underlying its employment traces directly to Bailey. Rapid deployment, modular configuration, adequate capacity deployed quickly beats perfect capacity deployed slowly. The philosophy proved more enduring than any specific hardware. Donald Bailey received recognition that came late but was heartfelt. He was appointed Officer of the Order of the British Empire in January 1943, elevated to Knight Bachelor in January 1946, and received £12,000 from the Royal Commission on Awards to Inventors in 1948. Field Marshal Montgomery wrote that Bailey bridging made an immense contribution towards ending World War II, and that without large supplies of Bailey bridging, Montgomery could never have maintained the speed and tempo of forward movement with the 8th Army in Italy and the 21st Army Group in Northwest Europe. General Eisenhower similarly credited Bailey bridges as one of the three most important technological contributions to Allied victory, alongside the Dakota aircraft and the Jeep. This placed a simple steel bridge system in the company of vehicles that became iconic symbols of Allied capability. The Bailey Bridge was less visible but equally essential. Despite this recognition, Bailey remained modest. He continued working as a civil servant, eventually becoming director of the Military Engineering Experimental Establishment. He served on technical committees, including the Bailey Committee on House Interiors, from 1952 to 1953. He became Dean of the Royal Military College of Science at Shrivenham in 1962, serving until retirement in 1966. After retirement, he lived quietly in Bournemouth. Neighbours knew him as a polite, unassuming elderly gentleman, not as the man who had changed military engineering forever. He rarely discussed his wartime work. When asked about the bridges, he typically deflected credit to the engineers who built them and the soldiers who used them. Bailey married twice. His first wife, Phyllis Amy Andrew, whom he married in 1933, died in 1971. They had one son, Richard Henry. In 1979, Bailey married Mildred Stacey, his housekeeper and widow of Herbert William Crees. She survived him when he died at Street, Leonard's Hospital near Bournemouth on May 5, 1985. He was 83 years old. His death received modest notice in British newspapers. The Times ran a brief obituary. Engineering journals published longer appreciations. But for most people, the name Donald Bailey meant nothing. The bridges bearing his name were better known than their inventor. This anonymity would have pleased Bailey, who always maintained that credit belonged to those who used his design, not to the man who conceived it. His grave in Bournemouth has no memorial noting his contributions. The house where he was born at 24 Albany Street in Rotherham still stands but bears no plaque. No statue commemorates him. No museum displays his original models and drawings. For a man whose invention was used millions of times and saved countless lives, physical monuments are remarkably absent. Yet his legacy spans rivers on 6 continents. Bailey bridges still carry traffic in remote regions. The design he created remains in production. The modular bridging philosophy he pioneered defines modern military engineering. His influence on military doctrine, engineering practice, and ultimately on history itself, exceeds that of generals whose names fill history books. The story of Donald Bailey and his bridge illuminates several timeless principles. First, that elegant simplicity often surpasses sophisticated complexity. Bailey's bridge succeeded not because it was technically advanced, but because it was appropriately simple. Every component was as basic as it could be while still functioning. This simplicity made production easy, logistics manageable, training straightforward, and field use reliable. Second, that the right solution depends on understanding the actual problem. Bailey didn't try to build a better traditional bridge. He recognized that traditional bridges were wrong for the problem of mobile warfare. He solved a different problem than previous engineers had attempted. This reframing enabled innovations that solving the traditional problem never would have achieved. Third, that modular systems provide flexibility that integrated systems cannot match. Bailey's insight to build a bridge-building system, rather than individual bridges, created adaptability that made the design universally applicable. Engineers could configure Bailey components for any span, any load, any terrain. This flexibility proved more valuable than any amount of specialized optimization. Fourth, that good design enables ordinary people to accomplish extraordinary things. Bailey bridges weren't built by engineering specialists with advanced training. They were built by regular soldiers with basic instruction. The design made complex engineering accessible to non-specialists. This democratization of capability multiplied the system's effectiveness far beyond what specialized equipment could achieve. Finally, that sustainable solutions must account for the entire system, not just the hardware. Bailey bridges succeeded because the design integrated with production capacity, logistics infrastructure, training programs, and tactical doctrine. The bridges worked because the entire ecosystem around them worked. This holistic approach to problem-solving distinguishes truly effective solutions from merely clever ones. Donald Bailey never sought fame. After the war, he lived quietly in Bournemouth, working as a civil servant until retirement. When he was knighted in 1946, neighbours were surprised. The unassuming man they saw at the bank or walking his dog had changed the course of World War II. He rarely discussed his wartime work. He maintained that the bridge's success belonged to the engineers who built them, not to the man who designed them. He died on May 5, 1985, at age 83. His legacy spans rivers on 6 continents. Bailey bridges still carry traffic in remote regions. The design he created in 1941 is still in production. The modular bridging philosophy he pioneered defines modern military engineering. The Bailey Bridge fundamentally changed how military forces thought about obstacles and mobility. Before Bailey, a destroyed bridge was a significant barrier requiring specialized equipment and extensive time to overcome. After Bailey, a destroyed bridge was a minor inconvenience requiring a few trucks, some infantry, and several hours. The bridges at Remagen became symbolic of the larger story. When American forces captured the damaged Ludendorff Bridge on March 7th, German High Command believed they could still destroy it and contain the bridgehead. They launched everything they had at that bridge: artillery bombardment, Luftwaffe bombing, special forces raids. For 10 days, German forces focused on destroying one bridge. They succeeded on March 17th when the damaged structure finally collapsed, killing 28 American engineers. But by then, 3 Bailey-type bridges were operational at Remagen, with 2 more under construction. The German effort to destroy one bridge had failed to stop the crossing, because the crossing didn't depend on one bridge. It depended on a system that kept building bridges faster than they could be destroyed. The story of Bailey Bridges is ultimately about solving impossible problems through disciplined creativity. The problem seemed impossible. Build bridges strong enough for tanks, light enough for infantry to carry, simple enough for rapid construction, adaptable enough for any situation. The solution required abandoning traditional assumptions about how bridges should work and reimagining the entire concept. German engineers who watched Bailey Bridges appear at every river crossing understood they were witnessing something new. Not new technology, new thinking. The Americans weren't building better bridges through superior materials or more powerful equipment. They were building adequate bridges faster and more flexibly than anyone thought possible. The bridges American engineers built across European rivers from 1942 to 1945 weren't just steel and pins. They were proof that simple, flexible solutions, properly designed and executed, can overcome any obstacle. They were testament to the courage of engineers who built under fire because soldiers depended on them. That is how American engineers won the Battle of the Bridges. Not by building better than the Germans. By building faster, simpler, and more flexibly than the Germans could imagine possible. The Bailey Bridge proved that sometimes the greatest victories come not from overpowering the enemy, but from thinking about the problem in ways they never considered. From finding elegant simplicity where others see insurmountable complexity. From building bridges not just across rivers, but across the gaps between impossible and inevitable.